Welcome to Momentum, Knowledge in Motion, and thank you for joining us for Episode 5. Today, we're diving into the fascinating world of quantization techniques for large language models, a topic that is gaining significant traction in the field of AI. Let's kick things off with our first paper. QAMBA 2 is an innovative post-training quantization framework specifically designed for state space models, or SSMs, and it's making waves in the field of AI by enhancing scalability and efficiency. Developed by a collaborative team from institutions like the University of Texas at Austin and Cornell University, QAMBA 2 is all about optimizing performance while significantly cutting down on memory usage by a whopping 4 times. One of the standout features of QAMBA 2 is its support for multiple bit width configurations, including W8A8, W4A8, and W4A16. This flexibility allows it to be effectively deployed across various platforms, whether in the cloud or on edge devices. It addresses performance gaps that have been a challenge for existing quantization methods, ensuring that models can run faster without sacrificing accuracy. The framework employs advanced techniques like sort and cluster and per-state group quantization, which enhance the precision of quantization for input-dependent parameters. This means that QAMBA 2 not only preserves the order of channels, but also maintains channel and state persistence, which is crucial for its effectiveness across different bit width configurations. This adaptability is key for optimizing performance in diverse deployment environments. One of the clever strategies QAMBA 2 uses is the sort and cluster technique, which takes advantage of the channel persistent property of SSMs. This allows for effective disentanglement and clustering of heads, leading to optimized weight reordering and improved scaling factor calculations. As a result, it achieves efficient 8-bit quantization, boosting performance across a range of applications. QAMBA 2 also integrates selective SSMs, which dynamically adapt parameters based on the input, allowing for a smart prioritization of information. This adaptability is vital for enhancing quantization precision, especially when dealing with sensitive input parameters. The framework employs advanced methods like Hadamard transforms to further optimize performance and minimize quantization errors. When it comes to performance metrics, QAMBA 2 shines with impressive latency improvements for Mamba 2 models, achieving speedups between 1.08 times to 1.19 times compared to FP16 across different sequence lengths. It also significantly reduces model sizes with configurations like W8A8 and W4A8, enhancing overall efficiency in deployment scenarios. Moreover, QAMBA 2 employs offline Hadamard matrix fusion, which optimizes input and output projections for better computational efficiency. This technique, combined with its mixed precision quantization capabilities, maximizes throughput and reduces latency, making it robust across various tasks. Extensive testing on platforms like A5000 and Orin Nano 8G has validated QAMBA 2 performance, showcasing significant latency improvements. For instance, in the W8A8 setting, it achieves a remarkable 1.80 times reduction in time per output token for Mamba 2 8B. It also demonstrates superior memory efficiency, outperforming previous frameworks while maintaining robust generation speeds. However, the evaluation on the MMLU dataset reveals some trade-offs. While the W4A8 configuration strikes a balance between prefilling and generation speed, it faces challenges with generalization. On the other hand, W4A16 maintains better generalization despite a slight increase in latency. Lastly, QAMBA 2 tackles the complexities of quantizing the embedding and output head alongside W4A8 blocks, which can often become memory bottlenecks. Experiments indicate that even larger models can maintain accuracy on the Lambda dataset despite these quantizations, enabling effective deployment on edge devices with limited memory through its flexible bit width configurations. Now, let's move on to the second paper of this podcast episode. Today, we're diving into a fascinating paper titled LLMPi, Optimizing LLMs for High Throughput on Raspberry Pi, brought to us by a research group from the Department of Computer Science and Engineering at the University of South Carolina. This work introduces LLMPi, a groundbreaking framework designed to optimize large language models, or LLMs, specifically for Raspberry Pi devices using innovative quantization techniques. So, what exactly does this mean? Well, LLMPi employs post-training quantization across various bit widths, which is a fancy way of saying it reduces the size of the model without sacrificing too much accuracy. It also incorporates quantization-aware training for bitnet models, which helps in fine-tuning these models to perform efficiently on devices with limited resources. The results are impressive, showing significant reductions in energy consumption and computational overhead. The paper goes on to explore several model compression techniques, including pruning, knowledge distillation, and low-rank factorization. It highlights advancements like LLMpruner and QLoRa, which work hand-in-hand with LLMPi's quantization strategies to enhance efficiency and shrink model sizes. This combination is crucial for developing highly efficient LLMs that can thrive in constrained environments. Now, let's talk about the architecture of decoder-only LLMs. The authors emphasize the importance of attention mechanisms and feed-forward networks, or FFNs, in these models. They detail how MAT-MUL operations are processed iteratively during inference, and how caching can significantly boost efficiency. Optimizing these operations, especially through quantization, is key to improving LLM performance on devices with limited resources. One of the standout features of this paper is the introduction of a K-quantization approach. This method applies multiple quantization levels, think W8A8, W6A8, W4A8, and W2A8, to optimize memory usage and throughput in conversational AI applications. The authors provide experimental measurements that reveal dynamic power, latency, and total power across various LLM configurations. For example, they found that the Llama 1B model achieves an impressive 14.78 tokens per second in Q2 quantization, a significant leap from just 3.81 TPS in FP16. This showcases how effective quantization can be in enhancing real-time AI interactions on devices with limited processing power. Energy efficiency is another critical aspect discussed in the paper. The authors present metrics like tokens per joule, TPJ, and words per battery life, WBL. Notably, the Llama 1B Q2 model achieves the highest TPJ at 5.18, indicating substantial energy savings. These metrics highlight the practicality of using quantized models for real-time applications in power-constrained environments. The paper also analyzes Nubia scores across different LLMs, revealing an interesting trend. While aggressive quantization often leads to a drop in accuracy, some models, like Phi-3B, manage to maintain high scores even at lower bit widths. This finding underscores the importance of model architecture in mitigating accuracy loss during quantization, which is crucial for real-world applications. Moreover, the effectiveness of quantization-aware training, or QAT, is emphasized as a means to preserve accuracy during extreme quantization. For instance, the BitNet07BQ158 model achieves a Nubia score of 0.36, demonstrating that with the right strategies, we can maintain performance even under significant constraints. Lastly, the paper acknowledges support from the National Science Foundation under grant number 2,340,249 and references various works that contribute to the understanding of LLM optimization. It also touches on recent advancements in edge AI, such as real-time transformer inference and efficient deployment on edge TPU accelerators, which complement LLMPi's framework. Next up, we have our third paper to discuss. The paper titled Sustainable LLM Inference for Edge AI, Evaluating Quantized LLMs for Energy Efficiency, Output Accuracy, and Inference Latency, comes from a collaborative research group that includes experts from SINTEF in Norway, Singapore Management University, and Oslo Metropolitan University. In this study, the authors dive into the world of quantized large language models, or LLMs, specifically looking at how these models can be optimized for edge AI applications. The focus is on three main areas: energy efficiency, output accuracy, and inference latency. The researchers emphasize the pressing need for sustainable AI practices, arguing that by optimizing LLMs, we can significantly cut down on energy consumption while still delivering solid performance. One of the challenges they tackle is the issue of quantization itself, which can sometimes lead to a drop in performance. To address this, the authors designed a robust experimental framework to evaluate various quantization techniques. Their findings are promising, suggesting that innovative approaches to quantization can improve model efficiency without sacrificing accuracy. This is a key insight for anyone interested in sustainable AI deployment in edge environments. The researchers conducted experiments using 28 different quantized LLMs sourced from the Llama library. They utilized datasets from the NeurIPS 2024 challenge to assess a range of capabilities. To measure energy consumption, they employed a jouloscope on a Raspberry Pi 4, allowing them to explore critical research questions about energy savings, accuracy trade-offs, and inference speed across different quantization methods. Their comprehensive evaluation of quantized LLMs on edge devices systematically analyzes the energy accuracy trade-off. They also delve into how various datasets and tasks can influence the performance of these quantized models. This research significantly enhances our understanding of model quantization techniques, including post-training quantization and various quantization methods, all of which support sustainable AI practices. The authors explore several quantization techniques, such as KV-cache quantization and Quantization-Aware training, QAT, which help improve model adaptability. By experimenting with different bit widths like FP16 and INT8, they demonstrate how these methods can optimize energy efficiency and inference latency while keeping accuracy loss to a minimum, an essential factor for edge deployment. They introduce balanced quantization strategies like Y=M, which optimizes memory efficiency and accuracy for mid-range hardware, and Y=L, which focuses on accuracy for high-end systems. The paper also highlights the importance of energy monitoring tools, stressing the need for precise hardware-based measurements, such as those provided by jouloscope, to effectively profile energy use in AI applications. The study poses 3 critical research questions regarding how model quantization impacts energy consumption, accuracy trade-offs, and inference speed for LLMs on edge devices. By utilizing datasets from the NeurIPS 2024 challenge, the authors ensure a representative evaluation, sampling tasks that enhance the robustness of their findings on quantization techniques. They employed a diverse set of datasets, including Common Sense QA, Big Bench Hard, and Truthful QA, to evaluate model performance across various tasks. Specific sampling methods and accuracy metrics, like exact match and Rugel, were implemented to ensure a thorough assessment of quantized LLMs in real-world scenarios, bolstering the study's validity. The paper provides a detailed overview of the quantized LLMs used in their experiments, categorizing them into 3 families: LLMA 3.2, QN 2.5, and Gemma 2. Each model variant, with parameter counts ranging from 494 million to 2.6 billion, employs various quantization types, including FP16 and lower bit options, all optimized for edge AI applications. Lastly, the authors investigate weight-only quantization formats, referred to as QXKY, which significantly reduce memory requirements, making them ideal for edge applications. They analyze the trade-offs between different precision levels, such as FP16 and INT8, and how these impact energy consumption and accuracy. As we continue, let's explore the insights from our 4th paper. The paper titled Quantization Hurts Reasoning, an empirical study on quantized reasoning models, comes from the research group at Huawei Noah's Arc Lab, with contributions from authors at Shenzhen International Graduate School, Tsinghua University. This study dives deep into how quantization affects reasoning models, particularly focusing on the DeepSeek R1 distilled QN and LLMA families. The researchers found that while lossless quantization is achievable, using lower bit widths can significantly hurt accuracy. They discovered that factors like model size, the origin of the model, and the difficulty of the tasks being tackled play crucial roles in performance. Interestingly, they also noted that strategic scaling can enhance outcomes, which is a key insight for developers working with these models. One of the standout points from the study is the performance of reasoning models in complex tasks, such as multidisciplinary question answering. However, these models often struggle with increased inference overhead, which can lead to excessively long outputs. To tackle this, the researchers explored various compression techniques, including quantization, pruning, and knowledge distillation, with quantization emerging as a favored method for balancing model size and performance. The paper introduces a quantization function, Q(b), designed to optimize model efficiency by mapping values to low-bit integers. This approach significantly reduces model size and memory access requirements. The study examines different quantization strategies, such as weight-only, KV-cache, and weight-activation quantization, each contributing to improved computational efficiency while still maintaining performance across reasoning tasks. A particularly interesting technique discussed is the chain-of-thought (COTI) data, which enhances reasoning efficiency. The researchers also delve into methods like token budget and direct performance optimization, DPO, to manage output lengths effectively. These strategies work hand-in-hand with quantization, highlighting the importance of empirical studies to find the right balance between efficiency and accuracy in reasoning models. The evaluation of quantized DeepSeek R1 DL-QAT models across various reasoning benchmarks revealed that performance takes a hit when bit widths are reduced, especially for smaller models. For instance, the accuracy of the 1.5B model dropped by over 10% with lower bit widths, emphasizing the critical relationship between model size and the effects of quantization. The study recommends using 4-bit quantization for KV-cache, which achieves lossless performance on larger models with minimal accuracy drops. For smaller models, an 8-bit quantization is suggested to maintain performance across tasks. The researchers identified AWQ and FlatQuant as the best algorithms for weight-only and weight-activation quantization, respectively, enhancing efficiency while addressing the impacts of task difficulty. Additionally, the paper analyzes how models trained through different methods perform under quantization. The study also sheds light on the output lengths of quantized reasoning models, revealing that aggressive low-bit quantization can lead to longer generated outputs, particularly in smaller models like DeepSeek R1 DL-QAT 5B. The researchers examined scaling, effects on performance, and latency, emphasizing the need for cost-effective quantization configurations to optimize accuracy. Finally, the paper explores the intricate relationship between model size, latency, and accuracy. Larger models, such as QW-Q32B, tend to outperform smaller ones like QN7B in terms of accuracy, despite having increased latency. The benefits of 4-bit quantization for improving accuracy-latency trade-offs are highlighted, enhancing reasoning efficiency across various tasks. Now, let's transition to the 5th paper. The paper titled Achieving Binary Weight and Activation for LLMs Using Post-Training Quantization presents an innovative framework aimed at enhancing large language models, or LLMs, by achieving 1-bit precision for both weights and activations while keeping performance loss to a minimum. At the heart of this framework is a technique that employs Hessian-aware grouping combined with an expectation maximization (M)-based scheme. This approach not only surpasses existing quantization methods, but also demonstrates a significant reduction in errors, pushing the boundaries of what fully binarized models can achieve. One of the key innovations is the Binarized Weight and Activation (BWA) attention framework, which enhances the standard attention module through a 2-level grouping strategy for weight binarization. This strategy is particularly effective for fully connected layers, which are notorious for consuming large amounts of memory. By allowing Boolean operations in the inner loops of computations, the framework significantly speeds up inference and reduces memory usage. The framework also introduces a fine-grained grouping strategy for weight quantization, utilizing 2 quantization parameters per group. This not only boosts accuracy, but also keeps computational costs manageable. Additionally, a scaling factor balancing strategy for activation binarization optimizes performance through efficient bitmap operations, refining the quantization process while preserving the integrity of the model. An interesting aspect of this framework is its handling of outlier activations, which are quantized using 8 bits to ensure minimal overhead. This clever approach limits outlier channels to just 3%, allowing for efficient implementation without sacrificing overall model performance. The algorithm-structured approach for weight quantization leverages a Hessian matrix for optimal grouping and employs an M algorithm for iterative refinement. This flexibility in weight representation significantly enhances computational efficiency and maintains model performance during inference. Experimental results showcase the framework's effectiveness across various models, including Llama 1, Llama 2, and Vicuna, with marked improvements in perplexity and zero-shot question-answering accuracy. The W+1 A1 times 4 method consistently outperforms FP16 and other quantization techniques, proving its robustness across diverse language tasks and datasets. In evaluating the framework, researchers used the massive multitask language understanding (MMLU) benchmark, comparing it against state-of-the-art methods like Atom, QAT, and BiLLM. The findings reveal that the W+1 A1 times 4 setting significantly outperforms these baselines in perplexity and zero-shot tasks, demonstrating superior stability and efficiency. Ablation studies further highlight the importance of minimum distance quantization and fine-grained grouping in enhancing model performance. Particularly in experiments with Llama 17B, these techniques help mitigate performance collapse in W1+1 A1 times 4 quantization, while the Hessian weighted distance metric and binarized residual decomposition refine accuracy, optimizing overall model efficiency. The paper also references significant advancements in the field, including the Vicuna chatbot, which achieves 90% of ChatGPT's quality, and various quantization techniques like GPT-Q and DL-QAT, which contribute to improving model efficiency. These developments underscore the ongoing efforts to optimize large language models, ensuring they remain competitive and effective across a range of applications. Moving forward, we have the 6th paper to share with you. The paper titled Optimizing Large Language Models, Metrics, Energy Efficiency, and Case Study Insights, authored by Taniat Khan, Sorer Modi, Shana Raza, and Sedef Akinli-Kakak from the Vector Institute in Toronto, dives deep into the environmental implications of large language models, or LLMs. At the heart of this research is the pressing need to address the energy consumption and carbon emissions associated with these powerful AI systems. The authors explore various energy-efficient optimization techniques, with a particular focus on quantization. This method has shown remarkable potential, with the case study revealing that it can cut energy consumption and carbon emissions by up to 45%. The paper doesn't just stop at presenting these techniques. It also provides a comprehensive analysis of carbon emissions during both the training and inference phases of LLMs. The authors evaluate existing metrics for measuring emissions and introduce a practical optimization framework designed to significantly reduce energy usage while still maintaining the performance of the models. This framework serves as a valuable guide for those looking to develop sustainable AI solutions. One of the standout contributions of this research is the introduction of LLMQAT, which integrates quantization during the training process. This innovative approach, along with discussions on local inference optimization, aims to enhance energy efficiency while ensuring that accuracy remains intact. To assess the effectiveness of these optimizations, the authors employ standard evaluation metrics such as precision and recall. They carefully analyze the performance trade-offs that occur post-quantization, while also tracking energy usage to estimate carbon footprints. The findings indicate that optimized models can function effectively even on resource-constrained devices, which is crucial for broader accessibility. Interestingly, while there were slight improvements in precision and recall, metrics like accuracy and the F1 score experienced minor declines. This highlights an important consideration: the need to strike a balance between energy efficiency and predictive performance, tailored to the specific requirements of different applications. The paper also includes practical examples, particularly in sentiment analysis, showcasing how these optimization techniques can be applied in real-world scenarios. This not only illustrates the feasibility of greener AI solutions, but also emphasizes the potential for these methods to be adopted across various domains, paving the way for a more sustainable future in artificial intelligence. Next, we'll delve into the seventh paper. The paper titled DL-QAT, Weight-Decomposed Low-Rank Quantization-Aware Training for Large Language Models, comes from a research group at Advanced Micro Devices, Inc., AMD, in Beijing, China. Now, let's dive into the exciting details of the DL-QAT method. This innovative approach enhances quantization-aware training specifically for large language models by leveraging weight-decomposed low-rank techniques. What does this mean for us? Essentially, it allows for a significant reduction in computational demands, making it easier to work with these complex models. One of the standout features of DL-QAT is its ability to adjust quantization groups and utilize low-raw matrices, which leads to impressive performance gains. For instance, when tested on the MMLU benchmark with the LLMPi model, DL-QAT outperformed previous methods by a notable 4.2%. This showcases not just efficiency, but also the method's effectiveness in adapting models to new tasks. The optimization process in DL-QAT is quite clever. It breaks down the training into two phases: group-specific magnitude training and weight fine-tuning. This ensures that the parameters are represented accurately, which is crucial for maintaining performance. In fact, DL-QAT surpasses baseline methods like Ka-Low-Raw by 4.2% on MMLU and 5.5% on LLMeval, all while requiring fine-tuning of less than 1% of the parameters. Now, let's talk about the QA-Low-Raw method, which builds on the earlier Q-Low-Raw approach. It introduces a high-precision group-wise bias to improve efficiency without compromising accuracy. However, it does face some challenges, particularly with accuracy degradation when the quantization granularity increases. DL-QAT addresses these issues effectively through its dual-phase optimization, ensuring robust performance across different quantization levels while keeping resource requirements low. When it comes to quantization updates, DL-QAT starts with established values for scale and bias, which are then frozen. The method optimizes parameters through its two-phase approach, ensuring optimal performance within the quantization space. This not only enhances efficiency, but also significantly cuts down on computational costs, achieving state-of-the-art results across various benchmarks. Speaking of benchmarks, DL-QAT shows remarkable performance across a variety of tasks, including MMLU and Common Sense QA. It excels particularly in zero-shot and few-shot settings, achieving impressive scores like 44.6% on ArcSy and 78.5% on HelloSwag. These results highlight the method's versatility and effectiveness in real-world applications. Moreover, experiments with the LLMPi model reveal that the weight fine-tuning strategy proposed in DL-QAT significantly boosts accuracy across different quantization settings. With only 1% of the parameters being trainable, DL-QAT can process up to 17,669 samples per hour, showcasing its superior resource efficiency compared to traditional quantization-aware training methods. Finally, recent studies by researchers like Ashkbuz et al. And Detmers et al. Have further explored advancements in quantization techniques, emphasizing the importance of outlier-free inference and efficient fine-tuning. These contributions reinforce DL-QAT's position as a leading method in the evolving landscape of quantization-aware training, making it a significant player in the field of large language models. Now, let's take a look at the eighth paper in our lineup. The paper titled Gradual Binary Search and Dimension Expansion, a general method for activation quantization in LLMs, comes from the research group at CEA List, part of Université Paris-Saclay, with contributions from Fabrice Rassello, who is affiliated with multiple institutions including UNIV, Grenoble Alpes, and INRIA. This research introduces an innovative quantization method specifically designed for large language models, or LLMs, utilizing Hadamard matrices to tackle the challenges posed by outliers in activations. The authors employ a technique called gradual binary search, which allows them to achieve effective 3-bit quantization for both weights and activations. One of the key insights from the paper is the unique difficulties that arise from activations in transformer architectures. These challenges are primarily due to outliers that can complicate traditional quantization techniques. To address this, the authors propose the use of rotation matrices in conjunction with Hadamard matrices, which helps manage these outliers effectively. The paper also delves into the issues caused by extreme activation values in LLMs, which can lead to performance drops when quantized. Techniques like LLM-Int8 cluster these outliers for separate quantization, while other methods such as SmoothQuant and sync tokens are introduced to manage these spikes. The authors emphasize the importance of visualizing the sources of outliers to enhance understanding and develop effective mitigation strategies. A significant contribution of this research is the introduction of the Paley algorithm, which generates Hadamard matrices under specific conditions, enhancing the quantization process. This method allows for the integration of non-power of two matrices with weights, optimizing performance while keeping computational overhead low. The paper details Algorithm 1, which outlines the gradual binary search method aimed at optimizing clipping ratios for quantization. This algorithm iteratively refines projections by assessing model performance against a dataset, ensuring that it converges within a defined threshold. The synergy between Hadamard and rotation matrices further bolsters the management of outliers, reinforcing the effectiveness of the proposed quantization framework. The authors establish the optimality of Hadamard matrices in reducing outliers through Theorem 3.2, highlighting that higher embedding dimensions can enhance this reduction. They propose a method for increasing embedding dimensions through zero padding, which improves outlier management without significantly increasing computational costs. The paper illustrates an architecture pipeline where dimensions are expanded, improving token representation in a high-dimensional space of 4096 plus D dimensions. The results show that the proposed QAT method, combined with gradual binary search, consistently outperforms traditional quantization methods across various metrics, leading to significant improvements in perplexity and benchmark scores for different models. In terms of results, the gradual binary search method demonstrates a notable enhancement in quantization performance, achieving up to a 6% improvement in perplexity across various models. For instance, the Mistral 7B model reaches an impressive 61.32% accuracy, showcasing the advantages of this approach and confirming the benefits of dimension expansion within the QAT framework. The paper also discusses the implications of dimension expansion on model performance, achieving up to 68.95% accuracy for the Mistral 7B Instruct model, although this comes with high computational costs. To address this, the authors introduce group local rotation, which enhances inference speed by applying Hadamard matrices to subtensors, optimizing performance in high-dimensional multi-layer perceptrons while effectively managing resource constraints. Finally, the paper provides theoretical proofs that support the effectiveness of Hadamard matrices in quantization. It demonstrates that normalizing these matrices preserves their beneficial properties, enhancing energy redistribution in high-dimensional spaces. The proofs also show that the application of rotation matrices can effectively manage extreme values, reinforcing the robustness and optimality of the proposed quantization framework in handling outliers. We're almost there. Let's discuss the 9th paper. Today, we're diving into an exciting paper titled StableQuant, Layer Adaptive Post-Training Quantization for Speech Foundation Models, brought to us by a research group from the Department of Electrical and Electronic Engineering at Yonsei University in Seoul, South Korea. So, what's the big idea behind StableQuant? This paper introduces a novel method for post-training quantization, specifically designed for speech foundation models, or SFMs. These models, like Hubert and WAFDVEC2, 0, are crucial in the realm of speech processing, but they can be quite hefty in terms of size and computational demands. One of the standout features of StableQuant is its ability to remove outliers during the quantization process. This is key because outliers can skew the data and lead to a loss of important information. By focusing on the unique characteristics of SFMs, which often use CNN-based feature extractors and transformer layers, StableQuant tailors its calibration methods to fit the varied activation distributions found in these models. Now, let's talk about the nitty-gritty of how StableQuant works. The paper details a systematic procedure, outlined in Algorithm 1, that identifies which layers might suffer from performance degradation when quantized. It uses a technique called percentile clipping to optimize scale factors, which helps in preserving as much information as possible during the quantization process. When it comes to performance, StableQuant really shines. The researchers conducted a comparative analysis, and the results are laid out in tables II and III of the paper. They show that StableQuant outperforms traditional quantization methods, particularly when operating at lower precision levels, like W8A8. Lastly, the references in the paper point to significant advancements in self-supervised learning and quantization techniques for speech models. The foundational works on Wavdevek and Hubert are particularly noteworthy, as they inform the methodology behind StableQuant, reinforcing its innovative approach to enhancing the performance and efficiency of speech models. In summary, StableQuant represents a significant step forward in making speech foundation models more efficient without compromising their performance, paving the way for more accessible and faster speech processing technologies. Finally, we'll wrap up with our 10th paper. The paper titled Optimizing LLMs for Resource-Constrained Environments, a survey of model compression techniques, authored by a team from Google, dives into a pressing challenge in the world of AI, the resource demands of large language models, or LLMs. While these models are incredibly powerful, their hefty requirements for GPU memory and energy make them less practical for deployment on mobile and edge devices. First up is knowledge distillation, a fascinating technique where smaller models are trained to mimic the behavior of larger, more complex models. This process not only reduces the memory and computational load, but also allows for efficient inference on devices with limited resources. The paper highlights different forms of knowledge distillation, such as self-distillation and multi-teacher distillation, which enhance performance while minimizing reliance on large teacher models. The survey also showcases several implementations of knowledge distillation, including GKD, Mini LLM, and DISTI LLM. These methods utilize innovative loss functions and adaptive learning strategies, leading to impressive performance improvements in smaller models, especially in tasks like translation and summarization, all while maintaining efficiency in constrained environments. Next, the paper delves into advanced quantization methods, such as ZeroQuant, which employs layer-by-layer knowledge distillation to achieve mixed precision formats like INT4 and INT8. This is a game-changer for reducing model size without sacrificing performance. Alongside quantization, model pruning techniques are examined, focusing on the removal of low-importance components to enhance efficiency, reduce size, and speed up inference, particularly for mobile applications. The survey provides a comprehensive comparison of various compression techniques, outlining their goals, advantages, and disadvantages. For instance, while knowledge distillation can enhance accuracy and generalization, it often requires a larger teacher model. Quantization significantly reduces model size, and pruning optimizes the parameter count. Emerging techniques are also highlighted, such as Mini LLM and DISTI LLM, which streamline the knowledge distillation process, enhancing model performance while simplifying training complexity. Innovative quantization methods like GPT-3, Int8, and BitNet are explored as well, optimizing matrix multiplication for transformers, which is crucial for improving efficiency and scalability when deploying LLMs on edge devices. Finally, the survey introduces smaller float representations like FP8 and NF4, which allow models to operate with lower bit widths while still preserving accuracy. This not only accelerates training and inference, but also enhances model efficiency, making it feasible to deploy LLMs on resource-constrained devices without significant performance loss. Thank you for tuning in to this episode of Momentum, Knowledge in Motion. We hope you found these insights on quantization techniques for large language models as intriguing as we did. Until next time, keep the momentum going in your quest for knowledge.